we're going to get started by setting up a new service. You're likely familiar with using Azure. You've got your subscription set up if you want to follow along. There are multiple ways, of course, to create a new service. This is one of the easiest ways, is going to the All Services and searching for your service. Your Data Lake Analytics requires three things to set up and run. Of course, you need a resource group. You need a name for the Data Lake Analytics account. The name actually needs to be a fully qualified, not a fully qualified domain name, but a routable and globally unique name. So you don't get to use dashes, periods, spaces, or other types of indicators in this like you might with some other services in Azure. In this way, it's actually quite similar in naming to both your Data Lake and your Azure Storage accounts. You need to pick the location. Data Lake Analytics is rather restrictive in the places where you can run it. We have 2 options in Europe and 2 options in the US. It's one of the things you want to think about when you start provisioning resources in Azure. If you haven't already, pick a region in Azure and put your services there and try to think out what type of services you want to use and what type of global distribution you'll want to use. Some services automatically are available worldwide. Some have specific matching pairs of regions where they'll be duplicated and you already have the built-in integration. And some services are either new or slowly rolling out to other regions, and you're restricted as to where you want to run them. You do want to keep services within the same region to minimize your latency and your data egress charges. The last thing we need is a Data Lake Storage Gen 1 account. The Data Lake that's assigned to this Data Lake Analytics holds a number of things related to the Data Lake Analytics service, including stats and compiled code and other data around the actual jobs that you've run, and a special feature called the USQL catalog, which can contain precompiled data, assemblies, and precompiled scripts so that for reuse later in your USQL jobs. So you have to have a Data Lake Storage Gen 1 account. You can create one, of course, here, as you can with most services in the portal. You can create dependent services right in the same blade. In this case, I've already set up EastUS2 demo dev for a storage account and preloaded some data there. So we'll have this going a little faster. One thing you want to consider when you've used Data Lake Analytics for a while, or you're considering spinning up a second or a third account for doing different types of processing, or having different divisions do different processing in parallel with each other, you can select monthly commitments once you have an idea what your usage is going to be. Rarely will you know what your monthly commitment will be when you first create your Data Lake Analytics account. So I'd always recommend that you choose pay-as-you-go in the beginning, but if you do pre-purchase AU hours, you can get a significant reduction in cost. And you can change to a pre-purchased pattern once you've set up your account in the 2nd, 3rd, 10th month, once you've settled down to a routine set of batch jobs that you're going to be running. It takes a couple minutes to get the service set up. Most of this is provisioning your initial cluster in the background and creating the metadata that's required to manage jobs in the Data Lake store that you choose. And now we've got our new service set up. In the beginning, the overview blade isn't that interesting. You can see we haven't run any jobs, we haven't spent any money, and we have no details about previous jobs. As you run jobs, this overview blade becomes more interesting, and it gives you an estimate of are you going to meet or exceed your pre-purchased usage, and gives you an estimate of how much you're going to be billed for at the end of the month. So this becomes an important screen later, especially if you want to see what's going on currently with your Data Lake Analytics service. First thing we're going to look at here is the Data Explorer. This is built into Data Lake Analytics blade here. It allows you to do two things: look at the uSQL catalog, which we'll look at later, and list your storage accounts which are connected and which provide the sources for data when you're running your uSQL jobs. Right now, we chose during the setup EastUS2 Demo Dev Data Lake Storage Gen 1 service as our primary storage for this. But you can add more data sources if you have multiple Data Lake Storage Gen 1s, or if you have Data Lake Storage blobs. Data Lake Analytics will read from either one of those. Today we're going to be focused on reading from our Data Lake Storage Gen 1 because it makes it much easier. I do talk about reading files from blob storage and writing files to blob storage in the book. Let's jump right in and create a new job. I found when I first started learning about this service that this was the most intimidating screen that you could get when doing this. It has the highest climb to get to at least comfort with this service. It's a lot like Visual Studio in that way. You are presented with a blank canvas, and you are able to put whatever you need to in here with very little feedback. It's also quite a lot like SQL Server Management Studio in that way. We have a couple of things that we get presented with here. We have a name for our job. We have the number of AUs, which is analytical units. This is the degree of parallelization that we can run our uSQL job with, from 1, which is the basic and just has one node, up to 32 and more, depending on how many you want, how much data you have, how many steps in the analysis you need to do, and how much money you want to spend to shorten the processing time. We'll go over that a little bit later once we have a couple of jobs where it makes sense to analyze. So let me open up first script here. And show you what this looks like. This is a fairly simple script. It's got 3 main sections, which is what you'll see in most every uSQL job that you run. The first section is reading files into memory. The reading uses the extractors class, which has a method for the type of file that you're going to be reading from. It has a definition of the file or files that you want to read in. It defines the fields and the field types that your data will be stored in when it's imported, and it defines a variable called a row set variable, which references the data in memory. Something to note, the @ symbol defines a declaration of a row set variable. Actually, almost any variable in here, especially a row set. We've got 2 different commands that will create row sets. The extract command, which will read from files in the Data Lake store, and a select command, which will read from other row sets and create row sets. So now that we have our first section defined as reading from a CSV into a row set with a particular set of fields. By the way, these fields have to match what's in the file that you're reading. So for example, we have 5 fields here defined in this extract statement for this row set. There needs to be 5 fields in the CSV file that we're reading from. The uSQL job will do a conversion from the data that it reads row by row into this row set, and it will do a best case job using the C# language definitions for converting the data in the field to this data type in this row set. You could define all of these as strings, and your string data would import into strings. But you can use some of the power of C# to automatically convert strings in your data file into more interesting and powerful data types, which give you more options for subsequent processing. Now that we've got this first section defined, we can look at the second section, which is our analytics analysis processing. In this case, we're doing a fairly simple analysis, which is give us a count of this badge ID field usage per day. We're actually using a C# function here to flatten this event time, date time data type into a string, which is only the month, day, year for the D format. And any of you who are familiar with programming in C#, you can look up online the definitions for a lot of these shortcuts for the toString command. We're grouping this by badge ID, door ID, and event time in this format, month, day, year, so that we're going to get all of our raw data into this players row set. And then we're going to do an aggregate with a count, which is a new field, by grouping all of these fields up. And we'll put that analysis output into the daily ag row set. This is a new row set separate from the players row set, which is holding our raw data. Two things to note here on this select statement. The first is you can generate new rows or new fields in a row at any point in your select statement, but all of them must have any new fields or any reuse of a field must have the as attribute assigned to that new field with a text description or a text name for the new field. In the extract statement, we define the original field name and the field type. We continue to use those field names that we defined above here in the select statement when we're reading from that row set called players. But with both of these, an aggregate here of count, we have to give it a name with the as attribute. We're calling this one access count, and we're spitting out a formatted string from this event time, date time field. We're actually giving it a name with the as attribute of access date. You need to separate all of these fields with commas, and you need to conclude or end each statement with a semicolon. All of the statements in your USQL job will need to terminate with semicolons. All right, one thing I'll note as well, all caps words are reserved words in USQL, and that actually includes words that have more than one capital letter at the beginning. So capital AC, sess date, would throw an error because this is being read as a reserved keyword and not having a match. So you can't use all caps words as names in USQL. Keep that in mind. The third part of this USQL script is the output. The format of all data handling USQL jobs works the same. Read data, do some processing on data, write data. There is no intermediate work with data in memory in a GUI, work with data and write back to the original files, or read data, work with data, and then stop. All USQL jobs which work with data have to have an output statement as well at the end to output the data. Otherwise, the compiler will actually throw an error and tell you that this job doesn't basically do anything rather than just spend money reading data into memory. All of your data processing jobs will have an output command using the outputters class. Like the extractors class, you've got several types of built-in file types that you can read from: CSV, TSV, and plain text, which actually allows you to define all of your separation characters, your in rows, and various other settings on the file import and export. So with step 3, writing out to files, we have to use the output command and specify the row set that we're outputting. In this case, we have 2 row sets defined in this job: the players row set here at the start and the daily ag row set here. You can create multiple row sets throughout your job, and often that is the easiest way to process and understand and structure a USQL job so that you can read the job and know what it's going to be doing. And occasionally you can get benefits from multiple staging of processing, where processing in a single row set command either takes a long time or would force a single node to do all the processing, which then slows down the parallel processing of the overall job. In this case, we have the raw row set here that was used from the extractor, and we have a process row set which holds our aggregated data, and the daily ag row set is the one we want to write out. We'll have a using command like we did for the extractors, which defines the file type we're going to get plus some parameters. In this case, we're going to output a header which will include the file names that are defined in the row set that we're writing out. One extra step that this output uses that the extractor did not use is a variable defining the file that we're going to work with. In this case, we have a string variable called out, which defines a path to a folder and a file name for our processing here. In the extractor statement, we said we'll look in the staging folder, demo folder, and read access_00.csv. And in our outputter, we're going to go to the curated/demo/v1 folder and write daily access count single.csv file. So now that we've defined these 3 sections, let's go ahead and submit this job to run. In this case, I've selected only a single AU because this job is not using a lot of data. I've uploaded a data file, which we'll take a look at here in a moment, called access_00.csv, which has 5 million rows, and it's about 300 megs. So we're going to be reading that data in here in a moment. So the process of submitting a USQL job gets your cluster ready to go. It submits the USQL to a .NET compiler, which converts the SQL language, C# language, and USQL into actual .NET code, which then runs on one or more nodes in the cluster. And the Data Lake Analytics service is managing spinning up the cluster, spinning up all of the nodes, running the compile process, distributing the code to all of the nodes, in this case just one, and each of the nodes handles reading of the data files and doing any intermediate processing and doing the subsequent and final processing and writing out the files in the end. As you can see, we have a update of how the job is processing here. We spent 26 seconds prepping, which was reviewing the USQL code for errors, doing a compile, checking for compile time errors, and then submitting that job to the cluster. If we have multiple jobs running and we don't have any available AUs in this Data Lake Analytics service, then we may actually have the job queued for a few moments or multiple hours. And then once there are enough available AUs to run the job, then it's submitted to one or more nodes in the cluster, and then it begins to run. This job ran for 51 seconds, actual processing of data reads and writes, and now it's completed. We have 100% progress on here. We can see the script that we submitted here. We can take a look at the data that was read and written. inputs and outputs here. And because these are CSV files, various types of text files, we can actually get a preview of the data here in the window. You can see this file had a header row with these IDs, and here's the data in it. In our outputs, here is the file that we wrote out. You can see it also has a header row, since we defined that in the outputter. And you can see the text format of the data in the file here. You can see we've grouped these up and grouped them by door ID and access count. But you can see they're a bit random here because we didn't define any type of ordering for these. Last thing we can look at here is the AU analysis screen. This gives you can use this to determine how efficient your job ran, and is there improvements you could make if you were running this job a second or third or multiple times to balance how fast it will run against how much it will cost to run. In general, once you get to a certain level of data, running a job at 1 AU is always going to be the most efficient. It will run as long as required to get the entire job done, up to 6 hours per node, but it will not take advantage of any parallelization, as in read multiple files, write multiple files, or do multiple filters and calculations in memory on multiple nodes when it's running. It will only use a single node and run sequentially from start to end. We're going to look a little bit more at this when we run some more jobs. At this point, let's go back to new job screen and run another job. As we saw before, for running a job, we need a job name, a number of AUs, and a script. Now that you've seen how we structure the USQL job with our input, our calculations, and our output, you can have some idea what we'll see for another job. So this job, quite similar to the previous job, though we've introduced another string variable here. As you can see, just like we did for the outputters, we can use a string variable to define the files that we want to read or write. In this case, the n variable is going to be used in the extractor to define this particular field, or this particular file to read in. And you can see this would run exactly as the previous job ran. But what if we've got more than one file that we want to read in? Well, in that case, USQL provides a wildcard notation for defining multiple files. It's best practice to use a string variable to define your ins and outs targets for your files. It also makes it a bit easier to actually build one of these wildcard statements if you need something more complex than just star.star. In this case, we've replaced the _00 single file name of access _00.csv in the previous script with curly braces and a star. The curly braces define your wildcard statement, and the asterisk or star is interpreted by the extractor class as being take any value that fits with the rest of the string, defining the path to the file. So if we take a look at our data explorer here, straight from the job, we can take a look in the staging folder, demo folder, and you can see there are actually 7 files here defined, access _00 through access _06. And with the access underscore curly braces star format here, we will read in access underscore 00 through access underscore 06 into our extractor statement and into our player's row set. What this means is all of the data in all of these files are going into a single declared row set, so they can all be addressed and read and processed in a single command, whether that's select aggregations with other types of SQL commands or written out to a single file. In this way, you could actually aggregate various files of the same type into larger files. Say one thing for data lake analytics efficiency and in general, big data processing pipelines, larger files tend to read and write more efficiently than smaller files. So if you are planning your data collection processing and you're going to end up with thousands of 5 and 10 meg files in your data lake, you're likely going to be introducing inefficiencies in the pipeline processing later on, where having tens of 100 meg files or ones and twos of gig files actually improves the efficiency of processing in your batch analysis pipelines later on, whether that's Data Lake Analytics or HD Insight or Databricks, any of your other types of processing. Most of these are based on HDFS and other types of Hadoop background services. So Hadoop is better at reading larger files and can break down larger files into parallel reads for faster reads and faster processing. That goes for the Data Lake Store and Azure Storage as well. Both of these do break your files down in the background into smaller extents so that the services themselves can stream from disk in multiple pipes to get your data faster into whatever service is reading it in. This is especially important in Data Lake Analytics, where we can use immediately parallel processing for reading these files and writing the files out, so that if we have multiple nodes available, we can either read multiple files at once if they're small enough, or we can read from multiple simultaneous streams from the same file because of the way Data Lake Store, and to a certain extent, storage account blobs are split across multiple backend storage services. That's an aside. Generally, you want your file sizes for best efficiency to be between 250 megabytes and a gigabyte each. But Data Lake Analytics will read files larger than a gigabyte, I think larger than a terabyte. I think it's something like 6 terabytes for the max. Don't quote me on that.